This video is on section 9.2 notes, operations with matrices. So since we're doing the sections a little bit out of order, this is our first section on matrices, and so I wanted to do a little bit of introduction before we really got into the operations. So first, a matrix is a rectangular array of numbers that's arranged into rows and columns. It's often used to represent tables or systems of equations. So here's an example of a matrix. The elements are the numbers within the matrix, so the specific numbers that you can see here. They're typically labeled based on the row and the column. So these are rows go horizontally. These are the columns go vertically. And so this element is row 1, column 1. This element is row 1, column 2. This element would be row 1, column 3. So row 2, column 1, row 2, column 2, row 2, column 3. Row 3, column 1, row 3, column 2, row 3, column 3. So those are the different elements within the matrix. Dimensions, the size of a matrix or the dimensions of a matrix is written as the number of rows by the number of columns. So rows by columns. So this would be a 3 by 3 matrix because there's 3 rows, 3 columns. All right, so for the first set of examples, it just says to determine the dimensions or the size of each matrix. So this matrix, matrix A, has 3 rows and it only has 1 column. So this would be a 3 by 1 matrix. This has 2 rows and 3 columns, so 2 by 3. And this matrix has 4 rows and 2 columns, so this would be a 4 by 2 matrix. If you wanted to know the element B21 in matrix B, you would look at the second row, the first column. So second row, first column is this right here, so that element would be -2. The value of element C12 in matrix C, you would look at the first row, the second column. So first row, second column, that's a value of -3 for that element. What is the notation used to identify the location of the 1 in matrix A? So here's the 1. That would be in the third row in the first column. So this would be A, third row, first column. All right, so that's just kind of an introduction. We've got the things that we need to know about the dimensions, labeling the elements, kind of recognizing which element is which. With matrix operations, we have a few different operations we're going to learn about. The first is adding and subtracting, and it's pretty intuitive. So when you add and subtract matrices, they have to be the same size. So this means they have to have the same dimensions. Same number of rows, same number of columns, so that you can add the numbers or subtract the numbers that are in the corresponding position. So here we have a 2 by 2 matrix, and we're adding a 2 by 2 matrix, and so our resulting matrix is going to be a 2 by 2. So I'm going to have 5 plus 2 is 7, 2 plus -4 is -2, -9 plus 6 is -3, and 1 plus 0 is 1. Over here, I have a 2 by 3 matrix subtracting a 2 by 3 matrix, and so my resulting matrix is also going to be a 2 by 3. 6 minus 10 is -4. 8 minus -18 is 8 plus 18, so that's 26. 23 minus 1 is 22. -2 minus -6 is the same as -2 plus 6, so that's 4. 5 minus 9 is -4. 12 minus -7 is the same thing as 12 plus 7, so that's 19. And so there's our resulting matrix. All right, on the next page, it says to solve for each variable. So here we're not adding or subtracting, we're just looking at 2 matrices that are equivalent. And we're going to use that information to solve for the different variables. So we have x and y and z. So x is in the top left position of the first matrix, or it's in row 1, column 1, and so row 1, column 1 for the other matrix is a 2. So we know that x equals 2. Over here, we know that 3y is going to equal 4. Sorry, 3 minus y is going to equal 4. And so that gives us an equation we actually have to solve here. So I'll go ahead and subtract the 3 over to the right side. So negative y equals positive 1. And then I can divide by a negative on both sides, and I get y equals negative 1. And then last, we have a z and a 9, z and 9 in this position, and so we know that z equals 9. So those are our 3 variables. Also fairly intuitive. Last, we have an example that has matrix addition as well as some scalar multiplication. So they're just saying to take matrix A and multiply it by 4, take matrix B, multiply it by 3, and then add those matrices together. So 4A is going to be negative 12, 8, 20, negative 28, negative 36, 0. 3B is negative 15, 0, 9, negative 3, 0, negative 12. And so 4A plus 3B would be negative 27, negative 31, 8, and negative 36, 29, and negative 12. All right, last we're going to look at an application problem. So this is taking a table of information and then using a matrix to represent it. So it says the table below shows the number of transistors and resistors purchased by a manufacturer from suppliers A and B for the first week of January. It says write the data in a 2x2 matrix, and we're going to call that matrix S sub 1. So S sub 1 is 400, 600, 800, 500. Okay. To find matrix S sub 2, the entries are all 10% larger than the corresponding entries in S sub 1. So S sub 2, we're going to take S sub 1 and we're going to make all of those entries 10% larger. So 10% larger would be 100% plus 10%, which is 110%. And if we think of that as a decimal so that we can use a scalar multiplication, kind of like this right here, that decimal would be 1.1. So what we're going to do is we're going to take S sub 1 and we're going to multiply it by 1.1 to get S sub 2. So we've got 400 times 1.1 and 600 times 1.1, and we can already kind of see the pattern. 800 times 1.1, 500 times 1.1. So we can write our values there. 440, 660, 880, 550. Okay, so there's our S sub 2. If S sub 2 is the supply matrix for the second week of January, find S sub 1 plus S sub 2. Okay, so S sub 1 plus S sub 2 means we're going to be taking 400, 600, 800, 500. we're going to be adding S sub 2. And when I add those together, I get 840, 1680, 1260, 1050. Okay, and then it says explain what the entries represent. So the entries for S sub 1 were the number of transistors and resistors purchased by a manufacturer from suppliers A and B for the first week of January. So this table is still going to have the same types of information. It's still the number of transistors and resistors purchased by a manufacturer for suppliers A and B. We still have that piece. So I'm going to write that. It's the number of transistors and resistors purchased by a manufacturer from suppliers A and B and now we have to determine when were these purchased. So it says this first table that we had was for the first week of January. So that's what this matrix represents, is the first week of January. And then S sub 2, all the entries that were 10% larger, these are for the second week of January. So if we added them together, that just means that this is the number of transistors and resistors purchased from suppliers A and B for the first 2 weeks of January. So matrices are one of the most probably applicable things that we learn about in math because we've got tables of information, we've got equations with information. This would be a way we could kind of program them into computers and work with them. So they're not very exciting when you look at them this way, but they are a great way to kind of organize information and work with information. You just have to be mindful of what the rows represent and what the columns represent, so that when you work with them and you do your computations, when you end up with some sort of solution matrix, you understand what the different rows and what the different columns in that matrix are representing. So that's something to keep in mind when you work with application problems. But as you can see, adding and subtracting matrices is pretty intuitive, and all we're really learning here is how to organize the information. But as far as math goes, we haven't really learned anything complex.